yesterday. Yeah, we mostly did the group exercises. So today we're going to move on with this chapter, probably finish most of the chapter. If not, then we'll finish it off on Monday. But we're going to move to another topic which has to do with harmonic oscillation, and that is what we call waves. So let me share my screen here. There we go. So today, like I said, we're going to look at, first of all, these waves here. So what's a wave? So let me set this on oscillation. So this is our wave. Let me put this in slow motion. So basically, this is what we would call a wave. So a wave then is, we have some sort of disturbance from a source. So here I have a harmonically oscillating source. And then that source is then generating a wave. Okay? So notice here I actually have two different types of motion. So here there's the wave itself. So if I watch the crest of this wave, the wave here is moving to the right and it's moving at some particular speed. But if I look at the particles themselves, i.e. the medium is actually undergoing harmonic oscillation. So here, if I look at, say, this green piece of medium, this thing is simply oscillating up and down. So only harmonic oscillation. But the wave itself is distributed through the wave. So a wave is actually carrying both energy and momentum from the source. So the source itself has an energy, it has momentum due to the fact that it's harmonically oscillating. That then propagates or travels the wave down through the medium, carrying that energy and that momentum with it. But the particles of the medium itself are not moving with the wave. They're only moving in harmonic oscillation. So again, if I'm watching the particle, the green one, it's only harmonically oscillating up and down. It's not moving to the right at all. So the medium itself is not moving, but the wave itself is moving. It is generated. It is carrying information. It's carrying both energy and momentum. So if I pause this thing at some stage, what we can see then is that the wave itself has a sinusoidal or cosine curve to it, but the particle itself is also moving up and down with a cosine or a sine curve. So basically that tells us that we have two pieces of information. We basically have two different harmonic oscillations. We have harmonic oscillation of the particle itself moving up and down, which is happening in time, but then the wave itself looks like a cosine curve or a sine curve in space, which means that that also is basically a harmonic oscillator. So what this overall tells us then is that a wave is a combination of two different harmonic oscillators. It's a harmonic oscillation of the particle itself moving up and down, and it's also harmonic oscillation in position as well. So this is what we're going to be talking about for basically this chapter and next chapter. So the rest of this chapter, we're going to talk about waves in general. We're going to look at particular properties of waves, talk about different types of waves, talk about all the different things with waves. And then in the next chapter we're going to look specifically at sound waves. So we're going to apply everything that we're going to learn now to those particular types of waves, which are sound waves. So again, so a wave then is, again, it's harmonic oscillation of the medium itself, moving up and down. And then it's the motion of the energy and momentum being carried away from the disturbance by the wave itself. Okay? So we talk about the wave, what we really talk about is the motion of this portion as it's moving to the right. But again, it's built from harmonic oscillation of the objects moving simply up and down. So that brings us to waves. So a wave then is a sort of disturbance that propagates. Propagates is just a fancy term for travels away from the source. So in general, there are three different types of waves. So the first type is what we call a mechanical wave. So a mechanical wave is a wave which requires a medium. So for example, what we just looked at. An example of this would be a wave on a string. Another example would be an earthquake. Right? So an earthquake, we have the ground itself is shaking. Another one would be sound waves. Right? So here, sound is carried through the medium, which in this case would be air. The next type of wave we have is what's known as an electromagnetic wave. So an electromagnetic wave is actually an oscillating electric and magnetic field. Now this will make more sense when we get further into semester. But basically an electromagnetic radiation or light is kind of interesting. So what it is here's kind of a schematic of what light actually looks like. So what you have are an electric field, which here is the blue curve, and then you have a magnetic field. And what happens is that the electric and magnetic fields actually oscillate. They constantly change direction, but they're happening at a 90-degree angle from each other. So basically what's happening is, let's say the direction at which the wave is traveling in this direction is the Z direction. So the electric field then is oscillating in the Y-axis. The magnetic field is oscillating along the X-axis, and the oscillation of those two together create the light wave. Now, light, again, it's an oscillating electric and magnetic wave together, but light, interestingly, doesn't need a medium to propagate. So light does not need a medium to propagate, unlike a mechanical wave. So how do I know that light doesn't need a medium to propagate? How do I know this? What do you think?
Would it be that light still works in a vacuum?
Exactly. Space is a vacuum. We know we get light from the sun. We know the sun then gives us most of our energy that we have on the earth, gives us all the heat that we have, and it travels through space to us. So we know that it actually works in a vacuum. Very good, Derek. So this is because it can travel in a vacuum. A vacuum. There we go. The last form of, or type of wave, is actually what's known as a matter wave. So a matter wave is the fact that all fundamental particles, so things like protons and electrons and etc., all have actually a wave nature to them. So this is actually quantum mechanics. So what quantum mechanics actually says is that all objects has a wave property to it. So all matter has a wave property. Now, of course, if we were talking about us, we also have a wave property to us, but it turns out that the wave nature that we would actually see for light is, or that wave nature is so small that we just don't actually see it. So even though we also have a wave nature, it's just ridiculously tiny and we don't actually notice it, we don't actually see it. So, but anyways, anything which has matter actually has a wave property to it. So again, this is what actually quantum mechanics says. So things like chemistry all work on the basis of the fact that everything actually has a wave property to it. Now, as far as this class is concerned, even though this is true, we actually don't care. We're not going to talk about this. So I bring it up just because it is a type of wave, but again, as far as this class is concerned, we're not going to discuss this. So if you were taking something like modern physics, which I don't think any of you ever have to take, but this is something that you would actually discuss in that class. So for this class then, what that means is we're going to consider both of these types of waves. So for now, we're going to focus on these, the mechanical waves. This will be the subject of pretty much everything we're going to talk about through this chapter and next chapter. And then at the end of the semester, we'll come back to this type of wave. So we'll come back to electromagnetic radiation at the end of the semester. So again, so for now, we're going to talk about mechanical waves. And then at the end of the semester, we'll talk about electromagnetic waves. So pretty much everything we're going to talk about for this chapter, the remainder of this chapter will be applied to by the time we get to electromagnetic radiation at the end. So we're going to talk about it now, do some other stuff, and we'll come back to it. So you have to pull all that stuff back out, and you kind of think about all this different stuff again. Okay. So again, what a wave is, again, is this harmonic oscillation of the medium. The medium itself is harmonically oscillating up and down. The wave itself is carrying both energy and momentum away from the source, whatever is causing it to oscillate. But no medium itself is actually being carried in the wave. So the wave is being carried by the medium, but none of the medium is moving with the wave itself. So here's another question for you. How do I know that a wave carries both energy and momentum? So we have a wave, we know it. So how do we know it carries both energy and momentum? So it carries both energy and momentum. So how do I know a wave carries these things? So it carries both energy and momentum. So what do you think? How do I know this? Anybody want to be brave? So what do you think? How do I know a wave carries energy and momentum?
Since it's in motion, it has kinetic energy.
Okay, well, how do I know it has kinetic energy?
It has a velocity. We can calculate that by the frequency.
Okay, I mean, that's true, but think about, so for example, light. It turns out light actually does have momentum as well, but if you're thinking about, typically when we think about momentum, we think about something which has mass, which is moving. So it'd be mass times velocity, but yeah, I mean, we know it has a frequency, we know it has those things, so we do know it has momentum. Okay. So we'll write that down. So we know it has momentum since it's moving. Okay. Moving. Again, light becomes a little bit trickier because light has no mass to it, so it becomes a little bit difficult. But how do I know it carries energy, for example? You're right, it does have a kinetic energy, but again, how do I know that? So think about a wave. So think about, especially right now in the middle of the summertime, what happens if you go outside and you put your arm outside?
Sunburn?
Sunburn, right? So you have energy which is transferred to you from the sun, and that's being transferred via the light itself, right, by the wave. So good. So in this case, we know that it carries energy because, exactly, so we know that our skin is warmed by the light from the sun. So in this case, we know that it's carrying energy. And we know it's carrying momentum because if any of you ever boogie board or surfed or done anything like that, been knocked over by a wave in the ocean, in the lake, right? So that's happening because it's carrying momentum, right? So we know that waves carry momentum since not only is it moving, but it can knock us down. And I don't know how to spell knock. Okay. It can push us down. There we go. Push us down. We can surf, right? Things like this. Good. So again, the wave is the result, again, of some sort of disturbance. So again, here's my disturbance. That disturbance then creates energy and momentum, and then the wave itself carries that energy and momentum away from this source. Now, in general, this can happen in one of two classifications of waves. So typically, in general, I should say, we have two different classifications of waves. The first classification is what's known as a transverse wave, and the second classification is what's known as a longitudinal wave. So this demo here is actually a very good example of a transverse wave. So what a transverse wave is that the medium is oscillating perpendicular to the direction of travel of the wave. So here, my medium, my string in this case, the particles are oscillating up and down, but the wave itself is being transmitted or propagated to the right. So a transverse wave then is a wave where the medium propagates perpendicular to the direction of motion of the wave. So this is the transverse wave. So again, a good example of this, again, is the wave on a string. So again, my medium is propagating up and down. The wave itself is moving to the right. So this then would be a transverse wave. So good. So examples of this are, as we just said, a wave on a string. Wave on a string. Another example would actually be an earthquake. So here, the medium, which is the earth, vibrates up and down while the wave itself moves in one particular direction. Okay, so these are actually transverse waves. A longitudinal wave is a wave where the medium propagates in the same direction as the travel of the wave. So here, the medium oscillates in the same direction as the motion of the wave. So, example of that would be, keeping your guys' faces all the time here, would be, let's do this one first. So here, let's say this is a slinky. So what's going to happen then is that this hand is going to move back and forth in the same direction as the wave itself. And then here the wave is propagating, so you can watch the medium here move to the right. So this would be the wave as the medium is propagating or oscillating in the same direction. Here's another good example. So again, here these are my transverse waves down in this section here. So here what's happening is the medium is propagating or oscillating up and down, but the wave is being carried to the right. But in this top portion, this is then my longitudinal wave. So here my particles are oscillating right to left, and the medium itself is moving to the right. So again, down here, you can kind of see that a little bit better, where it has the red arrow. So here it's just showing the harmonic oscillation of the particles moving side to side, but the wave itself is being propagated all the way to the right. Another good example of that would be, let me use this one. So here, again, a slinky. So he's moving his hand back and forth. The wave then is being carried to the right, but the portions of the medium are actually oscillating right to left. In a transverse wave, he's now moving his hand up and down. So this is now causing the wave to propagate. Again, the wave is propagating to the right, but the medium itself is only oscillating up and down. So these are, in general, the two different types of waves. So we have a transverse wave. We also have a longitudinal wave. An example of a longitudinal wave is actually a sound wave. So an example would be sound waves. We'll talk more about this in the next chapter. But the way a sound wave works is I create what's known as a compression. For example, I clap my hands together. When I clap my hands together, that creates an overabundance of particles in a particular position, or in this actually area, it creates less particles because I pushed them out of the way, which pushes those particles out to here. Then I have a high pressure of particles. Nothing wants to be in a high pressure, so they move away from each other, which causes this section out here to then become a high pressure. They move away, which then propagates the wave outward. So here, in a sound wave, the particles are only moving side to side, not perpendicular to the direction of motion. So, anyways, these are our classifications of waves. So we have transverse waves and we have longitudinal waves. Again, a transverse wave is one where the particles oscillates perpendicular to the direction of motion. In a longitudinal wave, they move in the same direction as the motion of the wave. So next thing we want to look at is, okay, so now we know we have waves. So let's go back to our original demo here. And let's say what I want to know is how fast is this wave moving along the string? So the first thing I want to know is what is the velocity of the wave on a string? So this is the first thing we want to know. So how do we do this? Well, first thing, let's think of a string. So let's say this is my string. It's actually a power cord, but it'll work sufficiently enough. So what type of properties do my string have? Okay, well, first of all, we know our string has what? A mass, because if I take this and I let it go, it's going to fall down, right? So first off, we know our string has a mass. So M equals mass. What units does mass have?
Kilograms.
Kilograms, good. It also has a length to it, right? So my string has a length. So this string can have a length. Let's say L equals our length. And what units does length have?
Meters.
Meters, good. And finally, the last thing is, if I want to create a wave on a string, I have to pull on the string, right? So if I want to get a wave going through, I can do it this way. Right? So here I have a transverse wave. I'm plucking in this direction. But if I put more tension onto it, I can actually pluck it, and the wave will actually move faster as I pull more and more tension onto it. So the last thing we can have on here would be a tension. And what units does tension have?
Newtons.
Newtons, good. And what is a Newton by definition? You may remember what the fundamental units are that create a Newton?
Isn't it like, whoops, sorry, kilograms meters per second or square or something like that?
It is a kilogram.
Yeah.
Meter per second squared. That's right. Now, last question. What are the units of velocity?
Meters per second.
Meters per second, good. So basically, what we want to do then is come up with a meter per second from these quantities which the string has, the mass, the length, and the tension, by using dimensional analysis, right? So first of all, what we know is we want a meter per second. And then if we look at the newtons, what we see is we have a kilogram meter per second squared, right? So basically what that tells us is that the velocity is going to have to go something as the square root of the tension, right? Because the only way to get rid of that second squared is by taking a square root. Right? The other thing is we know the tension has a kilogram in it. So to get rid of that kilogram, we would have to divide it by the mass. So we're going to divide that guy by the mass, and then that's going to give us what? A meter per second squared. But to make it into meters per second, when we take a square root, we would have a square root of a meter per second. So we're going to multiply this guy by the length. So this says that the velocity of a wave moving on a string is actually given as the square root of the tension, which is the tension at which the string is under, times the length of the string divided by the mass. So this is the velocity of the wave on a string. Okay. Now, typically what we do is we rewrite the mass divided by the length as mu, where mu is what's known as the linear mass density. Which means that we're actually going to rewrite this then as the velocity is equal to the square root of the tension divided by the linear mass density. Okay. So this is the velocity of the wave on the string. Always okay? So let me write that on this page. So we know the velocity then is equal to the square root of the tension times the length divided by the mass, which is the same thing as the square root of the tension divided by the linear mass density. Now, let's make some observations of this. Let's talk about this a little bit. Observations. Observation number 1. The velocity goes up as the tension goes up. So if I put the string under higher tension, the speed at which that wave travels is going to be faster. So again, if here's my string, I don't have much tension into it, I pluck it, and my wave moves kind of rapidly, but not too fast. And then if I put it under more tension, and as I pluck it, my string actually has the wave move faster through it. Okay? So, question is, does this make sense? So if I put this under more tension, why does it make sense that the velocity goes faster? So if I have more tension, why does it make sense that the velocity is faster? That's my daughter, sorry.
Is it because they're directly proportional?
Sorry, Winnie, I can't hear you. Let me turn it up.
Because they're directly proportional in our equation?
That's true, but let's think of it more from a physical standpoint. So not like a mathematical one, but let's think about it from, you know, things like what we know before. So things like inertia and acceleration and things like that. So you're right. These two things are directly proportional. So we know that the velocity is proportional to the square root of the tension. But let's think about it more physically. So physically, why would it make more sense that the velocity would go up if I had more tension to it? So if I had more,
I'm sorry. Is it because like your sum of forces is equal to mass times acceleration? Your mass is staying the same. So when you increase the force, then the acceleration has to increase.
Exactly. Exactly. So here we know that what? If we increase the force, so as the force increases, the acceleration must increase, which means that what? The inertia increases as well. Good. Now, observation number 2, we can see that the velocity goes down as the mass increases. So why does that make sense? It's actually exactly the same reason what Callie said. So as the mass goes up, the acceleration has to go down, which means it can't move as fast. So here, as the mass increases, the acceleration must decrease, which means that the inertia decreases. Good. All right, good. So these are some observations we can make out of this. Now, one thing to point out before we move on is that what? Here we're talking specifically about this motion, the wave itself moving to the right. Now, turns out that the velocity at which the wave is moving to the right is independent or different anyways than the velocity at which the harmonic oscillator is moving up and down. Okay? So the wave here can move at a different rate than the particles are actually moving with their velocity. So again, we know when they're at their maximum displacements, they have 0 velocity, maximum velocity by the time they get back to the equilibrium position, and then a decreased velocity and then move out. So this is not the velocity we're talking about. We know how to describe this velocity. This is what we did in the first part of the chapter. So here we're talking about only the speed at which this is moving to the right. Okay? So we're talking about the wave itself, not the harmonic oscillation. All right, good. So now that we know that, let's do an example. So our example says that we have 2 strings. Each one is 15 meters long and are stretched side by side. So here's my string 1 and here's my string 2. Okay. And it says one string has a mass of 78 grams. That's the first one. And it's under a tension of 180 newtons. The second string here has a mass of 56 grams and a tension of 160. So it has less mass, but it also has less tension. So we're going to put a pulse on each one of these guys. The pulse then is going to move to the right in both cases. And we want to know which string has the faster pulse. So meaning which one has a faster wave. Is it going to be wave number 1 or string number 1, or string number 2 is going to have a faster wave? Then we want to know once the faster wave reaches the far end of the string, so once this pulse reaches here, let's say this one's the faster one, we want to know by how much time does it beat the second wave. So how much more time does the second wave need to reach the end of the string? Okay, so again, they're both 15 meters long. First one is 78 grams with 180 newtons worth of tension. The second one then is 58 grams with 160 newtons. So again, basically what we want to know is which pulse wins. So which pulse wins? Who's faster? Is it going to be wave 1 or wave 2? So which one is faster? Which one reaches the end faster? So before we do any math, let's just kind of guess. Which one do you think is going to be faster? Is it going to be wave 1, which again has 78 grams for mass, let's call that mass 1, with a tension Ft1 equal to 180 newtons? Or is it going to be wave 2, which has, I don't remember how much mass did it have? 58. Right, so 58 grams equals M2 with a tension Ft2 equal to 160 newtons. So just by looking at those numbers, which one do you think is going to win? So again, we're not going to do any math yet, but just which one do you think is going to win?
The second one?
The second one, okay. And why do you think that? Oop, I wrote 16 instead of 160. So why do you think that, Tara?
Oh, well, originally it was such a big change in newtons between the two, but I didn't realize you added a 0.
Yeah, I'm getting old. I forgot these things. So, well, just go with it anyway. So why do you think number 2 is going to win?
It's got less tension.
It's got less tension. Okay. Good. So who thinks that number 1 is going to win? Okay, Whitney, why do you think that?
I think that because of the tension, force is larger.
Okay, so you think because the tension is larger, we know that as the tension goes up, the wave moves faster. So you think because it has a higher tension. Okay, good. Well, let's find out. Well, before that, so who agrees with Whitney? Let me ask you that question instead. So who's going to agree with Whitney that the first one's going to make it there faster? Anybody agree with Whitney?
I do.
Okay. So you got one friend. Okay. How many agree with Tara that the second one's going to win?
I think I agree with her because of the mass by proportion. I think it's going to be a bigger number for the second one.
Okay. And so you think because the mass is so much smaller that the proportionality will be bigger and make it faster?
Yeah.
Well, let's find out. Good. So let's look at V1 first. So V1 we know is going to be the square root of Ft1 times the length divided by M1. So that's going to be equal to the square root of 180 times 15 divided by, that's grams, right? So that's 0.078 kilograms, because that's being kilograms. Plug in our numbers, what we find in this case then is that it moves at 186 meters per second. V2 then is going to be equal to the square root of Ft2 times the length divided by M2, which is then going to be equal to 160 times 15 divided by 0.058 with the square root. Plug in our numbers, what we find in that case is Tara was absolutely correct. The second wave wins. Yay. Okay. And the reason for that is actually exactly what Katie said, which is that it's actually the proportionality. So what you see is that even though string 1 is under higher tension, the mass is so much greater, which makes that proportionality factor smaller than what it was in the second one, which has a smaller tension, but the mass is so much smaller that gives it a greater proportionality factor. Exactly, it has less inertia to it when the mass. So part B now we want to know, okay, so now what we know is that coming across here, wave 2 is going to reach the end first. Right? So this is then going to be pulse 2. This guy's going to reach the end first. And now pulse 1 is going to be some distance behind it by the time it reaches the end. So what we want to know then is what is the change in time, delta t, before wave 2 here reaches the end. So this is what we want to know. Still good. So one thing is, we know that the wave is moving with constant speed. So if we look at our second kinematic equation, which says x is equal to x naught plus v naught times t plus 1/2 at squared, since the wave moves with a constant velocity, we know there is no acceleration, so this term is simply going to be 0. Okay. Which means that for each one of these waves, we can simply write that x is equal to x naught we can call 0. So that's just going to be equal to the velocity times the time. Okay. So this says then that the time it takes for the wave to travel across the length of the string then is going to be equal to the length of the string divided by the velocity. It's okay with this? So this means then that the change in time between when pulse 2 finishes and pulse 1, this is going to be equal to the time that T1 takes minus then the time that T2 takes. Right? So this is pulse 1 and pulse 2. And I'm writing T1 first because, again, it takes more time for it, so it's going to be a bigger number. So this is going to be the same thing then as the length of the string divided by V1 minus then the length of the string divided by V2. But we know the two lengths of the string are the same, so it's going to be L times 1 over V1 minus 1 over V2. Okay. So it's going to be the same thing then as 15 meters times then 1 over 200, oops, sorry, not 200, that was 180 something. That back here. Good, that was 186 minus 1 over 203, which works out to be about 0.007 seconds. So that means then as it takes the second, well, the first wave, 7 milliseconds longer to reach the end. So the change in time between the two is 7 milliseconds. So basically, if I was watching these two pulses, what I would notice then is that pulse 2 would reach the end. 7 milliseconds later, pulse 1 would reach the end. Of course, watching it, I wouldn't notice too much of a 7 millisecond difference. My eyes aren't that good, especially the older I get. So I would actually have to, be timing it using something else. But so good. So this is the speed at which a wave travels on a string. Right? So again, this has to do with the tension, and it also has to do with the mass of the string and also for the length of the string. So kind of show you that here. So one thing we do is, let's say I decrease the tension. So let's put this at a low tension. We put it back to normal speed. So here you can see the wave is moving to the right at normal speed with kind of a low tension. And now if I crank up the tension, the wave now moves much, much faster to the right. Right? As I crank up the tension, the wave itself moves much faster with the higher tension as opposed to the lower tension. I'm done. So the next thing we want to know is, well, how do we mathematically describe the motion of the wave? So what I want to know is, how do I describe what the wave is doing as it moves across the medium? So we're going to look at the mathematical description of the wave. Now, as we already said, what we can see by this type of wave which is moving, so this type of wave is what's known as a harmonic wave or a periodic wave or a traveling wave. So any wave which repeats itself over and over and over again, just like a harmonic oscillator, is called a periodic wave or harmonic wave or traveling wave. So this one's called a traveling wave because the wave is actually moving to the right. And we're going to see waves that don't actually move in a little while. But so, good. So here we've already said that what? We have the up and down motion of the medium itself. So we know that the medium is going to be harmonically oscillating, which means that we know that this thing has to be somehow proportional to cosine of omega t, right? This comes from the harmonic oscillation. But we also said that if we pause our video at some point, what we can see then is this thing also looks like a cosine or a sine curve in position as well. So what that also tells us is that this thing has to somehow be proportional to cosine of something times x, which comes from the position profile. So we know is that our description of our mathematical description of our wave has to include something which deals with time and something which deals with position. So we're going to write d of x of t. So what d is d is going to be the displacement of a piece of medium away from its equilibrium position. So basically here, the distance from this orange line to a piece of medium is what we're calling d. Okay? So let me draw that on here. So basically, if I was looking at the wave, so let's say this is d, this is x. So again, if my wave is, say, doing something like this, then d is this distance here. So it's the distance from the equilibrium position to the position of the medium. So this is my distance of d. Okay? So d then is describing the displacement away from equilibrium. So this is going to be equal to a, where a is going to be the amplitude. So that's going to be the maximum displacement that this thing has. So a, again, is going to be amplitude, same thing as it was for harmonic oscillation. Okay. So again, if I go back to my simulation, so that would be this portion here. So this is my amplitude. So that's the maximum distance away from equilibrium. Times cosine of omega t. So this is my harmonic oscillation portion. Minus plus k times x. We'll talk about k is here in a second. Plus phi. Okay, so phi again is our phase factor. So this was the same phase factor we saw for harmonic oscillation. So this just tells me again how my system starts at time is equal to 0. This is how system starts at t is equal to 0. Good. So let's write about some of these things. So again, omega here is some harmonic oscillation. So this is the angular frequency of the medium. T here is the time at which this is occurring. So this is just, if I'm looking at this, this is happening at, say, t is equal to 1 second. So this is just where that piece of medium is at 1 second. Okay, so this is just the desired time. X here is the location of the piece of medium. So basically all that means is pick your spot on here. So if I'm talking about this piece of medium here, then this would be, say, at 1 meter. So this displacement here is talking specifically about this single piece of medium and how this thing is actually oscillating up and down. Okay, and this is what X stands for. So X is talking about his up and down motion. Okay, so X here then is the specific piece of medium that I'm actually talking about, his location. So again, here, if I was dealing with this particular particle at 1 meter, then I would put in 1 meter here. Okay. Again, phi is the phase factor. So what is K? So K is going to be confusing because K is not the same K that we saw before. This is not the spring constant. This is a new quantity. So we're going to have to keep these Ks straight, basically, okay? So what is K? So K is what is known as the wave number. So the wave number, so based off of here, has units of radians per meter. Okay, so this is our K. So what is the meaning of K? So basically, what you can think of is the meaning of the angular frequency is how many oscillations does this thing make in a particular amount of time. So for example, if you said the frequency was 2 hertz, what that means then is what? In 1 second, this thing makes 2 full oscillations. That's what 2 hertz means, right? So what the angular frequency says then is how many angles or how many radians does this thing go within a certain amount of time. So what the wave number says is basically the same thing, is that it says is how many oscillations are there within a certain amount of distance. This is what the wave number means. So wave number then is equal to the number of oscillations in a meter. So this is what the wave number means. So basically means that what, if I was looking at the picture that I drew here, so this guy here, what we're basically saying here is that this thing starts off at 0. This is making what? A little more than 1/4 oscillations in a meter. So this would be our wave number. So the wave number then is a measure of how many oscillations there are in a given amount of distance, where the angular frequency is how many oscillations there are in a given amount of time. So this is our wave number. So again, here we have to be careful because this K is no longer the spring constant. It is what's known as the wave number. So unfortunately, in physics, as we'll notice as we move through the semester, certain variables have certain meanings depending on context. And we use those variables over and over and over again. For example, you have now seen K 3 times. Right? The first time you saw it was Boltzmann's constant back in 175 when it came to thermodynamics. The second time you saw it was spring constant. The third time you saw it is now wave number, and we're going to see it at least one more time when we get to electricity, which is what's known as the electrical constant, basically, okay? So each one of these Ks has a different meaning, so we have to keep in mind and determine which K we're talking about from the situation and what's actually going on, okay? But just because you see a K doesn't automatically mean it's spring constant. It could be Boltzmann's constant or the wave number or the electrical constant by the time we get to electricity, okay? So unfortunately, that's the way our book does it. So we have to stay kind of consistent with the way that the book does it. I would like to use a different variable, but also I don't want to confuse you when it comes to the book. So this is just convention. So unfortunately, we just have to keep these things in mind. Okay. So good. So this is how we actually describe a wave. So this says, again, that the displacement of a piece of medium is equal to the amplitude times cosine of the angular frequency times time, minus plus this wave number times the position of that piece of medium, plus then the phase factor. So what is this minus plus? So now we got to talk about the minus plus. So what does this portion mean? So the minus plus is in reference to the direction of propagation. So the minus plus tells me what direction is my wave moving. Is it moving to the right or is it moving to the left? Okay. So it turns out that the negative sign corresponds to a right moving wave. And the positive sign corresponds to a left moving wave. So when you see this written as d of x of t is equal to a cosine of omega t plus kx, that means your wave is moving to the left. If you see it as a cosine of omega t minus kx, that means it's moving to the right. Okay. So these plus and minus, again, refers to the direction of the wave. If it's a negative sign, it's moving to the right. If it's a positive sign, it's moving to the left. Okay. So this is our description of the wave. So A cosine of omega t minus plus kx plus phi. So this is our mathematical description of the wave. So let's talk about some more properties of the wave here. So here, our wave looks like what? If I plotted the displacement d versus time, again, we would have a harmonic oscillation. Let me draw it a little bit further. There we go. So again, we know that the distance from here to here is equal to the period. Right? So this is our period. So the period then is the time it takes to go from maximum to maximum or minimum to minimum, however you want to think about it. So this is equal to our period. In position, if I plotted the displacement versus position, again, I would have my wave look something like this. The distance now between crest to crest is now what we call lambda, where lambda is equal to the wavelength. So the wavelength then is the distance between two successive points which are the same. So again, if I'm talking about a crest to crest or trough to trough or a 0 to a 0, but the distance where it repeats its pattern again is what's called the wavelength. So the period is from the time it takes to repeat in time, and then in position, that's what we call the wavelength. Now, the amount of time it takes to go from a, say, crest here down to a trough back to the crest would actually be the same thing as a period, right? So if I think about this guy is oscillating up and down, he's going to go down all the way back up. That then is going to be a period, but that point is going to travel this distance, which is the distance of the wavelength. So basically what that tells me then is that the wavelength is equal to the velocity times the period. So for a general wave then, what this means is that the velocity of the wave is the same thing as the wavelength divided by the period, or since the period is equal to 1 over the frequency, oops, so I was going to write the other frequency, there we go. Then this is the same thing as the wavelength times the frequency is equal to the velocity of the wave. So this velocity here is general for any type of wave. Any type of wave. Where the velocity I wrote down earlier, so this velocity, which was the square root of the tension times the length divided by the mass, again, this is only true for on a string. On a string. So this velocity is only true when it's on a string, where the velocity we just wrote down is true for any type of wave. Okay? Now, what we also know is that the frequency is related to the angular frequency by 2 pi. And it turns out that the wavelength is related to the wave number by 2 pi. So it turns out that the wavelength is equal to the wave number, or 2 pi divided by the wave number. So if I use those in here, I can rewrite this then as 2 pi divided by the wavelength times then the angular frequency divided by 2 pi is also equal to the velocity. But my 2 pi's then are going to cancel. So this says that the velocity then is equal to the angular velocity divided by the wave number. So these are two velocities which are both general for any type of wave. It just depends on the information at which it is that we know. So we can either say the velocity is equal to the wavelength times the frequency, but that's also equal to the angular frequency divided by the wave number. So this is true for any type of wave. Just depends on what it is that we know, what we're given in the problem. Okay. So good. So let's do an example. So my example says that, here's my example, it says that we have a transverse wave on a string as described by the equation that d of x of t is equal to 2.2 centimeters times sine of 130 radians per second times time plus 15 radians per meter times position. So here it wants to know what is the maximum transverse speed of a point on the string. That's talking about the harmonic oscillation. What is the maximum transverse acceleration of a point on the string? And then how fast does the wave move along the string? So let's write all these things down. So good. So first off, we know that d of x of t is equal to, so what is that? 2.2 centimeters times sine of, there we go, 130 times t plus 15 times x. Okay. So my first question to you, even though it doesn't ask this in the question, is what direction is this wave moving? Is it moving to the right or is it moving to the left, based on what we just talked about?
Left.
Left. Good. This is a left moving wave. And again, it's left moving because this is a positive sign. Good. So from here, we can simply read off all of our parts. So what we know is that the amplitude in this case is equal to 2.2 centimeters. We know that the angular frequency is equal to 130 radians per second. So remember, whatever shows up in front of the t is the angular frequency. And we know that the wave number is equal to 15 radians per meter because whatever shows up in front of x is the wave number. Okay. So for part A, what we want to know is what is the maximum transverse velocity? Well, going back to harmonic oscillation, that's simply equal to the angular frequency times the amplitude. So from here, we know the angular frequency is 130. We know the amplitude is 2.2 centimeters. So that's equal to 130 radians per second times 0.022 meters, which works out to be 2.9 centimeters. Or sorry, meters per second. Okay, there we go. Meters per second. Part B wants to know what is the maximum acceleration. Well, we know the maximum acceleration is the angular frequency squared times the amplitude. So that's going to be equal to 130 squared times the 0.022, which then works out to be 371.8 meters per second squared. And then part C wants to know, well, what is the speed of the wave? Well, we now know the speed of the wave is either equal to the wavelength times the frequency, or that's the same thing as the angular frequency divided by the wave number. Now here, in the problem, we're given what the wave number is, and we're also given what the angular frequency is. So we can simply use those two. So it's going to be equal to 130 radians per second divided by 15 radians per meter, which is the same thing as 8.7 meters per second. So this is the speed of the wave. So again, the point here is to point out, again, that the velocity of the medium oscillating up and down doesn't necessarily have anything to do with the motion of the wave itself. So again, here, we're just in this situation here. We have this guy is moving to the left, even though it's moving to the right here. But again, the medium itself is oscillating up and down with a particular velocity. The wave itself is moving perpendicular to that with its own velocity. So those two velocities do not have to be the same. So here, the maximum transverse velocity is 2.9, where the speed of the wave itself is 8.7. Okay. How much time? We got 15 minutes. Okay. So, is everyone okay? Not too bad. So the last thing we'll start talking about today is, it turns out that we can add waves together to create new waves. So we can create new waves by adding together existing waves. This is what's known as superposition of waves. So we can create new waves by adding together pre-existing waves. So this is what music is all based off of, right? When you play a chord or a note, for example, when you strum guitar strings and you create a chord, you're having each wave vibrate with a particular frequency, but then the superposition of those together creates an overall chord. It creates a different wave because we can actually add these waves together. So let's see how this is going to work. So to do this, let's go back to here. Let me get rid of all this. So we're going to look at two different cases. So what I want to see here is I'm going to add a pulse. Okay, so I'm going to create a pulse, and we're going to look at two different scenarios. So the first scenario is we're going to have a fixed endpoint, which is what this is, which means that this endpoint here is not allowed to move up or down. So it's fixed in position. And then in the second case, we're going to look at, now we're going to have a loose endpoint, which means this thing is allowed to move up and down, and we want to see what happens. So let's look at the first case. So here we're going to have the fixed endpoint, and we want to watch what actually happens. So here's my pulse. I'm going to send that down. It's going to hit the boundary. Oh, sorry. Let me get rid of the damping. Let's do that again. Pulse, great. Slow motion. Let's try that again. So my wave comes in. It's going to hit the boundary. So what happened to the wave? So the wave is moving to the right initially. It hits the boundary, and then it gets what's called reflected. So this portion of the wave gets reflected back in. And what happened to the wave when it got reflected? Let's try that again. So initially it comes in, hits the boundary, and what happens to the wave?
It like flips to a minimum instead of a maximum.
Good. So when it gets reflected back in, it goes what we call out of phase by 180 degrees. Okay. So let's write that down. So for a fixed endpoint, the reflected wave is out of phase with the original by pi radians, or 180 degrees. So as Katie said, what happens is what? Initially the wave is moving in. Say this is my initial wave. Hits the boundary out here. And then afterward, it is flipped to a minimum, moving in the opposite direction with exactly the same amount of speed. Okay. So this is our boundary point. Good, so that's with a fixed endpoint. So let's look at what happens with an unfixed endpoint. Let's see what happens then. And then we'll use the superposition to try to figure out why this happened. Okay. So good, so let me release this endpoint, and let's happen with this one. So I'm gonna, again, send in the same pulse. It's gonna come in, hits the boundary, and then comes out. Let's try that again. And one more thing I want to kind of show here. So let me pause this and click on the point, just to point out something at the end. We'll talk about why this is in a second. So watch the boundary. Okay. So what happened in this case?
The reflected wave is in phase with the original.
Good. So here we go. Keep going.
But the endpoint went past the maximum before it came back.
Good. So we have the reflected wave is in phase with the original. What actually happened is at the boundary, the amplitude doubles. So if it's initially moving to the right with an amplitude of A, by the time it reaches the boundary, it actually has twice of that amplitude. And we'll talk about why that actually is. So again, let's draw a related little picture. So again, we have our wave here moving to the right, velocity v. Here's our boundary point. After it is reflected, it then is still in phase, moving with exactly the same amount of velocity. But by the time it reached the boundary, what actually ended up happening then is that the amplitude doubles. So if this had an amplitude of A, by the time it reaches here, it actually has an amplitude of 2 times A. So then amplitude actually doubles. So to understand why this is actually true, we're going to use this idea of superposition. So again, superposition says is that, again, we can create and construct a new wave by adding 2 pre-existing waves together. So let's go back to this case. So first, the unfixed or the fixed endpoint. So the way that we imagine that this is working is initially we have this wave moving to the right. This thing is going to move in from some position, heading towards the boundary. But then what we imagine is that somewhere out here, out in space, is we have another wave which is moving with exactly the same amount of speed, moving in the opposite direction with the opposite amount of amplitude, which basically means that initially this wave on the left is moving to the right with a velocity of v with a positive amplitude. So here this has an amplitude of A. This one is moving in from the right, moving to the left with an amplitude also of A, but it's out of phase from 180 degrees. Okay. So by the time these 2 reach at the boundary, what happens then is I superimpose these 2 waves on top of each other. So I'm going to get my blue one here. I'm going to get my green one here. But when I add these 2 amplitudes together, they cancel to give me 0. Right? So again, when I go back to my simulation, put this back on fixed endpoint. If I let this guy keep going to the right, again, the amplitude comes in, hits the boundary, the amplitude goes to 0 at the boundary, and then gets reflected backwards. So again, we're imagining is that somewhere way out here on the right, I have a wave which is moving to the left, which has exactly the same amplitude, exactly the same frequency, it's just out of phase by 180 degrees. So by the time they reach the boundary, they superimpose on top of each other, which in this case is if the phase is out of phase from the other one, then the 2 amplitudes subtract from each other. And I have the amplitude of 1 minus the amplitude of 2 is then equal to the total amplitude. So in this case, since the amplitude of 1 is equal to the amplitude of 2, then the total amplitude then is equal to 0. Okay. So this is then the superposition of our waves. In the second case, again, what we imagine is for the unfixed endpoint, again, this guy is moving into the right. Simultaneously out here, I have a wave which is moving left with, again, the same amplitude, the same frequency, but in phase in this case, so this amplitude is exactly the same as this amplitude. So by the time they reach our boundary here, then I get this guy is here, here's my green one, here is my blue one, exactly the same. So by the time they interfere with each other, we end up with an amplitude exactly twice the size. So when they interfere with each other in phase, in that case, my amplitude 1 gets added to my amplitude 2, or then the total amplitude. So in this case, amplitude 1 is equal to amplitude 2, which means the total amplitude is simply equal to twice of the original amplitude. So this case, where I have the fixed endpoint, this is what's known as destructive interference. So this is called destructive interference. So when two waves are superimposed on top of each other, they interfere with each other. And if they are out of phase with each other, then they interfere destructively. For destructive interference, then the total amplitude then is going to be the difference between the two amplitudes. So this is true for destructive interference. The second case, for the unfixed endpoint, this is what we call constructive interference. So constructive interference occurs when two waves interfere with each other, but they are in phase with each other. In this case, what happens then is that the amplitudes add together, so the total amplitude then is going to be the sum of the two amplitudes. So this is true for constructive interference. So we have constructive and destructive interference. Again, constructive is when the two waves interfere with each other at a single point, where they're in phase with each other, in which case it doubles the size of the amplitude or just increases the amplitude by the sum of the two amplitudes. For destructive interference is when I have two waves interfere at a given point, but they interfere in such a way that they're out of phase with each other, so they interfere destructively, decreasing the size of the amplitude. So this is called interference, constructive and destructive interference. This constructive and destructive interference can create interesting things, and one interesting thing it can create is what's known as a standing wave. So I'm going to mention standing waves. We'll pick this up on Monday and talk about the description of standing waves. But let's create a standing wave and let's talk about what actually happens. So basically what I'm going to do is I'm going to again turn this thing on, but I'm going to put it on oscillate. So what'll happen then is I'm going to have my wave initially moving to the right, so we're going to have that periodic right traveling wave. But using the same logic that we have here, we're going to imagine that on the opposite side, out in space somewhere, we have a wave which is moving with exactly the same amplitude from the left, but it's initially out of phase with that wave. So what's going to happen is I'm going to have one wave moving this way, one wave moving this way, but these two waves are going to be completely out of phase with each other, but with the same amplitude and the same frequency. But as they're moving, sometimes they're going to be moving with the same phase, and sometimes they're going to have out of phase with each other. So these two things will superimpose with each other, which is going to create which is called a standing wave. So let's see how this works. So again, here is my wave, my initial right moving wave moving to the right. Hits the boundary. It's then going to start to superimpose with the left moving wave moving to the left. And this creates what's known as a standing wave. Okay. So let's kind of watch that one more time. So again, first I start off with a right moving wave. On the left, I have a left moving wave over here somewhere. These two things now start to interfere with each other, which now creates what's called a standing wave. So notice the difference between a moving wave and a standing wave. So the traveling wave, the wave was actually moving to the right or to the left. But here, what's happening is by the time these two interfere with each other, the wave itself doesn't propagate anymore, right? So this piece only moves up and down in harmonic oscillation, and that is it. So this is what we actually call a standing wave. So standing wave is the interference between two traveling waves, which are interfering both constructively and destructively simultaneously. And again, watch what happens to the amplitude. So here, my initial wave has the same amplitude that we've sent in before, but now when they start to interfere with each other, when they're interfering constructively, the amplitude has now doubled. Okay. So when a standing wave is the interference between two traveling waves moving in opposite directions, which are both interfering constructively and destructively at different points along the string. That then creates what's called the standing wave, where the standing wave doesn't move in position. It moves up and down, but it doesn't move side to side. And that's what we call the nodes. Okay? So the nodes are, as this thing starts to reflect, I'll point them out to you. So for example, this point here is a node. So it's a node because as this thing is oscillating up and down, this point never goes away from zero. This is called a node. So the node is a point which is fixed in space at 0. So as this thing is harmonically oscillating up and down, all the points which are away from that, so for example, all these points here, these aren't nodes because they're oscillating up and down. But this point here, this point never moves up and down. It's always fixed at 0. So this is what we call a node. These points here, the ones which are oscillating with maximum amount of amplitude, these are what are known as antinodes. So a standing wave, scribble this down real quick. So standing wave. So this is the interference between two traveling waves. Moving in opposite directions. And these are described by fixed nodes. So the wave is not moving. Wave is not traveling. And they have fixed nodes. So basically, if I plotted this thing, so let's say I'm plotting this, then this point here, and this point here would all be what we call nodes. So these are locations that stay at 0 at all times. These portions, this portion here and this portion here, are what are known as antinodes. So these are portions which oscillate up and down at maximum amplitudes. Like I said, we'll talk more about this on Monday, but one more thing I want to show you is this is also true if I put a loose end on here as well. So just because I had a fixed endpoint doesn't mean that's what actually creates the standing wave. So if I have here, I can actually create the standing wave as well if I have a loose endpoint on the side. Okay. So having this loose endpoint, or having the fact that it's a fixed endpoint, doesn't necessarily create that standing wave. It's just the fact that I have two waves which are interfering with each other, which are moving in opposite directions. So again, here, notice I'm again creating the standing wave. I still have those fixed endpoints. I still have the fixed nodes. It's still oscillating with twice the amount of amplitude. But the difference now is that the endpoint can go up and down between twice the amplitude to negative twice the amplitude, where for the fixed endpoints, what happens in this case is that the endpoint is fixed at 0. The endpoint is a node, where in the other case, it's an antinode. Okay. So again, this is the basis of basically all musical instruments. We'll talk about these as we get more into sound, but different types of musical instruments will have different sorts of these. For example, I can have two unfixed endpoints. That would be something like a flute. I can have two fixed endpoints. That would be something which has a string, so something like a violin or a guitar. Or I can have something which has a fixed endpoint with an unfixed endpoint, which would be something like a saxophone. Okay. So, what is it? We'll start talking about this on Monday, but I just want to point this out, and then we'll pick up from there on Monday. So don't forget, no class tomorrow. Enjoy your 4th of July. Life will be great. Hopefully everybody has great plans. If it doesn't rain the entire weekend. So we'll see. So is everybody okay? Any questions on any of this before we kind of skid that?
Are there going to be any conceptual questions?
No. So I didn't post any yesterday because we didn't get to any of this. So I didn't, I had nothing really to ask at that stage. And I don't want to ruin your 4th of July, so I'm not going to ask any conceptual questions as well.
Okay.
So I will post them on Monday, though.
Sounds good.
Is there going to be a pre-lab posted at all for the next lab?
Yes, I'll do that probably today or tomorrow.
Okay.
Yeah. So we'll have a little bit to do over the 4th of July. We'll be okay. Everything's okay? Any other questions? Good. All right. Well, ladies, enjoy your weekend, your holiday weekend, and I'll see everybody on Monday. Bye, Kelly.